Alright, you guys, let's see. Happy Monday. If you can hear cartoons or sneezing and coughing in the background, that is my baby, my husband. Everybody's sick. Bear with me. I'm going to start doing section 9.3 via this video today. And then there is another video that's a full write-up over memes, and you have the opportunity today in class to watch both of those and take some notes. And that is the deal. I am going to push the quiz back to Thursday. Just so that we have Tuesday and Wednesday in class to go over free response problems together so that you can be ready for the quiz Thursday. Okay, so sorry for the wishy-washiness in the schedule. I hope you had fun at Fanboys on Friday. Of course, that's backfiring a little bit because now I'm sick today and the rest of my family is too, but we can still do this. Okay, so I do have everything written out already just so that my handwriting is nice and neat, but a couple of things we need to think about. So there's this thing called Table B. I encourage you to either grab one of those yellow sheets from the desk, just ask the sub for them. They're in the bottom folder of, or bottom drawer of the teacher desk, so that you can kind of practice finding p-values using the table. We are using Table B, not Table A. Remember, Table A is a bunch of z-scores and stuff. These are test statistics, they're T's. So you need to be looking at the second table. It's got DF along the left-hand column, and the confidence intervals or levels at the bottom, and the top is the p-values. So be looking at that table. You can also pull it up in Schoology if you want to. But there are ways to calculate these test statistics or these p-values based on test statistics. You can either use the table or you can use the calculator. So I've done, tried to explain both. Here's how to do it in the table. Here's how to do it in the calculator, which is much easier. Anyway, so what we're going to do is we're going to calculate this test statistic, and we've got a ho and a ha here. This is a one-sided test. Just make a note here that if it was a two-sided test, you would be doubling the p-value from the table. Just keep that in mind. I'll talk about that when I do the second one. But we have a sample size of 75. You know that that's going to be important because whenever we're doing a t, we need to know degrees of freedom, and it's n minus 1, so 75 minus 1 is 74. That's the degrees of freedom. Let's see, and we're given a test statistic of 2.33. So what's test statistic, you might wonder? So that's this thing that we calculate. We've done it in the first section, it was a z. In the second section when we did proportions, and remember that was our p hat, which is our statistic, minus the p from the ho, and then the statistic, standard deviation of statistic using the p from the ho. That is what we did in the second section. So here's how it changes when you're doing means. Remember, when you're doing means, you don't have a p. So we're using x bars and mu's. And again, this is the mu from the ho. It works very similar to the proportion from the ho, but it's just a mean instead of a proportion. And then this is the standard deviation of our statistic. We take our sample standard deviation and divide by root n. So this is what I'm talking about when I talk about test statistic. So they have already calculated the test statistic for us. It's 2.33. That's from plugging in all the stuff from the sample and from the problem that we are going to study. They've given you the test statistic 2.33. So you can either type this in the calculator to come up with the p-value. The way you do that is you go exactly the same places you go to normal CDF, except these aren't normal, these are t distributions. So there's actually a t-CDF option, and it works exactly the same way as normal CDF, but it's t-CDF. So make sure you choose the T option, t-CDF, and it's 2.33, shade to the right, degrees of freedom is 74, okay? And so there is a way to do this in the table. And so if you have a table in front of you, or if you're looking at it in Schoology, the test statistic of 2.33 with this degrees of freedom will give you a p-value 0.01127. Keep in mind that's pretty low. If we're using an alpha of 0.05, which we usually do, we would reject the ho. If we were using an alpha of 0.01, this is not too low, so we would fail to reject. Keep that in mind. This is not a full write-up. We're just practicing coming up with the p-values based on the test statistic. A lot of important vocab here, you guys. But anyways, how do you go do this in the table? So we've got our test statistic of 2.33. Degrees of freedom is 74. And you know how there's not a degrees of freedom 74 option in the table? Remember, you always round down. So the next one available is 60. So on the table, you are looking at the degrees of freedom of 60 column. And you have to look at all of those 4-digit decimals and find the one that is the closest to 2.33. As you can see, the calculator will give you something much more accurate, but what the table will give you, if you can find it, One of the test statistics in the degrees of freedom of 74 row is 2.099. Another one is 2.39. So our test statistic falls in between those two. And if you look up at the very top, those are p-values. That tells us that our p-value is somewhere between 0.02 and 0.01. And that's as good as the table can do, you guys. The calculator gave us the exact digit. Okay, so keep that in mind. If we were using an alpha of 0.05 and we know the p-values between 0.02 and 0.01, we would still reject, but the calculator can tell you exactly what that value is. So I'm going to do the same thing for the second one down here. We've got a ho and a ha. This is a two-sided one. Remember I said the most common mistake that people make in their calculations is in the event of a two-sided test, forgetting to double the p-value. And that's again why I wrote that up here. If it was a two-sided test, you always double the p-value. The reason for that is because, as you know, these t distributions, we come up with a test statistic like this example of 2.33 and we shade to the right. If it was a two-sided test, we would also have this area on this side. These are symmetric, but that is why you double the p-value, because the p-value gives this tail area. And so since you have two tails, that's why you have to double it. Keep that in mind. Anyways, where was I? We've got a test statistic of negative 0.051. And in this case, what I'm doing is TCDF. Since this is negative, I'm going to do the left tail first. Since this number was positive, that's why I did the right tail. Also, this is shading to the right, so it's telling me that I'm looking at the right tail, and that's why I did 2.33 to infinity. In this case, we have a negative test statistic, so I'm going to do the left tail, and then I will double it. So TCDF in the calculator, negative infinity to the test statistic of negative 0.51, and the degrees of freedom in this case for a sample of size 10, that means degrees of freedom is 9. It's n minus 1. Calculator gives you 0.311, double that thing, and you get 0.622. Is this too low? No way. This is a very large p-value. That is not too low. We would probably definitely fail to reject on that case. If you're looking at the table, you do have a degrees of freedom of 9 row, and so you're looking at all of those 2-digit decimal or 4-digit decimals in the table for the one that's closest to negative 0.51, and it gives you a p-value of 0.25, which tells us it's something a little bit bigger than a half. So go ahead and look up this digit as close as you can in the table with the degrees of freedom of 9. You're looking in that row. It is definitely less than 0.0703, which is from the table, which tells you when you double that, you're doubling your p-value of 0.25, which is going to be something bigger than 0.5. Remember, this is not the best, but as good as we can get based on the table. This is the exact number from the calculator. Either way, we would most likely fail to reject based on that really big p-value. Okay, so just keep in mind that this thing called a test statistic is a vocabulary word. For proportions, it is a z. And it's on the formula sheet. It says statistic minus parameter over standard deviation of statistic. So if it's a z, then you're using your p's. If it's a t, remember we use t when we don't know the standard deviation of the population. This is the calculations that we're using, and that gives us our test statistic. And then if it's a z, you're doing normal CDF in the calculator. We did that last section. If it's a t, you're doing TCDF in the calculator. There's a weird way to do it in the table also. That's the moral of the story. Moving on. Flip the page. Again, I do have a bunch of this stuff already written out just so that it's easier for you guys to see. But just copy stuff down kind of as I go through this. This isn't a full write-up. We're not defining stuff. We're not writing a conclusion. We're just checking conditions and calculating the test statistic and the p-value. So basically the important stuff of the write-up, missing a few steps. In this case, we've got a classic rock radio station claiming, here's our ho, to play an average of 50 minutes of music every hour. And so we are assuming down here, I'm going to write that the mu is 50 minutes. We're assuming that's true. Whatever they're claiming, we're assuming it's true. That's going to be our ho, and we are testing because we suspect otherwise. It seems that every time we turn the station, there's a commercial playing. Typical radio story. Am I right? That kind of means, in other words, you think they're playing less music than 50 minutes, and so that's why our ha is less than 50 minutes, okay? Notice I'm using mu's here because these aren't proportions, these are means. To investigate the claim, we select 12 different hours throughout the week, and we record what radio station plays in each of the 12 hours. So it's how many minutes of music is played each hour. And here are our statistics that we came up with. These are all of our different X values. They stand for number of minutes of music. Remember, we're suspecting that this 50 is inaccurate, so we've got 3 right away that are less than 50. That one's more than 50. Good for them. Congratulations, radio station. Less than 50, more, less, equal, less. It does seem like, just glancing at this data, that maybe they are lying about this 50 minutes, but let's test it. Okay, so random, independent, and normal. This is this typical stuff. Randomly selected 12 hours. We've got our 10% condition met. There's definitely more than 120 hours in a given week. Normal, it doesn't say up here if the population itself is normally distributed. Also, CLT can't apply. That is why I gave you all of this stuff. So here we've got a dot plot of the distribution. I wouldn't say symmetric, but I'm not also seeing any like extreme outliers or heavy skew. Here's the box plot, a little bit easier to see. Yeah, kind of slightly skewed, but I wouldn't say extreme. And again, no outliers. Here's the normal probability plot. Remember that these are z-scores on the y-axis. This is roughly linear, I'd say. So for that reason, no reason to doubt normality. And then remember, what we're going to say is safe to use T. All right, so that was a rundown of the 3 conditions. Remember, if this was a full write-up, we would define some stuff. We would write our opening sentence. Again, after we do all these calculations down here, we would conclude. This is not a full write-up. We're just answering some questions and kind of introducing what these are going to look like. But here we go. Compute the test statistic. That's the T. In this case, it's a T because these are means up here, and they did not tell me the population standard deviation of number of minutes played per hour of music. So that's why we're using a T for our test statistic. Here's the important stuff that we're given. The X bar, that's just the average of all of this stuff. You can type it into your calculator real quick. I would do one variable statistics. That gives you X bar and SX. So take a second and type that stuff in. Make sure you remember how to do one variable statistics. That's in the F4 menu under calculate. This is the X bar and this is the SX of these 12 data points. Degrees of freedom, 12 minus 1, which is 11. The calculator will ask you for that. Test statistic minus parameter over standard deviation of statistic. For proportions, this stuff changes. For means, this is what we're going to use. So our statistic is from the calculator. Remember, the mean is from the hoe. That's the 50. We're assuming that 50 to be true. Standard deviation divided by root 12. That gives us a test statistic of this. Remember, that kind of works like a z-score, although it's a t distribution, so those tails are fatter, so there's a little bit more area in those tails. But this is pretty far to the left. If you consider like 3 standard deviations to the left, it's kind of close to it. So the probability that t is less than or equal than that test statistic is 0.013. How do you get this in the calculator? T CDF. Okay, and remember that we're not doubling our p-value because this is a one-sided test. So we get this p-value. If you're looking this up in the table, you're looking at the degrees of freedom of 11 row, and you're looking for a test statistic as close as you can get to negative 2.5-ish. It's going to give you a p-value that's consistent with this, but not as accurate. If our alpha level that we're using here is 0.05, since nothing was given here, we would reject this p is too low. We reject the hoe. That means we do have evidence that this is true, that the radio station is playing less than 50 minutes. Okay, you guys, that was just a brief rundown. We're going to finish up some notes on Tuesday and Wednesday this week. Your quiz will be Thursday. Type this stuff into the calculator, practice, stop this video, and now go watch the next one that I put both in Edpuzzle. I'll answer all your questions tomorrow, okay? Thank you for your understanding, and have a great day.